This lesson leads on from our ideas of refraction, and this one is talking about total internal reflection. This term will become clear as we work our way through this lesson. So let's just take stock of what we know already. We know that when light enters from a less dense medium into a more dense medium, then as light strikes the surface, it bends towards the normal. And we're happy with our angle of incidence, our angle of refraction, and we can say sin I over sin R is our refractive index. Our refractive index, of course, is material dependent. It tells us how optically dense, how transparent or how not transparent a material is, so optically dense a material might be. Okay, and hopefully we've all sort of tried and manipulated this equation quite comfortably and successfully. Now that has dealt with light coming into a more dense medium. However, for the purposes of this lesson, what happens if light strikes from a more dense, maybe I should try more dense there, to a less dense medium? Then what takes place? I suppose that's the only difficulty we have with this topic. We're going from more to less dense medium, so we bend away from the normal. Of course, we have a larger angle there than this one. Now, in actual fact, you can sort of picture that as exactly what's happened previously. It's just that we don't like drawing it like that, because we like to look from things going from left to right. But that's exactly what's happened previously. We're just moving this way around. And if we hold those angles to be the same, R inside, I outside, then this equation does hold true. In other words, if you keep holding the idea of R is in the more dense medium and I is in the less dense medium, then we can keep the idea that sin I over sin R is N. And I think that makes sense if you keep remembering less dense is I, more dense is R, then this one equation is the only one you need to manipulate and hold on to. Okay, now there are three stages that we need to talk about here, because you can appreciate, as we increase this angle, R, so I will continue to increase, and it will get to a point where it actually gets to 90 degrees. Then what happens? So I suppose what we can say here is this is what's happening before that point. And in this case, light travels through. Transparent material. Now, what happens at this point where the light that's refracted is at 90 degrees? So what happens at that point? So this is refracted light at 90 degrees. Okay, now this equation changes slightly because, of course, remembering I less dense, R is more dense, our situation turns to sine of 90 divided by sine R is N. Well, N is the refractive index of the more dense material. Now sine of 90 turns to 1. So what we're left with is 1 over sine R gives us N, or even sine R is 1 over N. And then what you can say here is that this is a very special angle. This R is actually the critical angle. And that is all equal to 1 over n. So at this point here, which is known as the critical angle, light can no longer pass through. Light is trapped in the block. So we should say at critical, theta critical, light is trapped. Okay, bear in mind that equation there. Hold that equation in mind. Because what we'd say is light gets trapped in different materials. And of course, it's material dependent. So if I were to just write that down again, and I'll draw this around again. So there we go, theta critical. Let's just look at some refractive indices. Refractive index for glass is 1.5. The refractive index for water is 1.33. And the refractive index for diamond is 2.04. No, sorry, it's actually 2.4. So what would be the critical angles of them? Well, we said sine of theta critical is 1 over n. So then that must mean that the critical angle is going to be sine to the minus 1 of 1 over n. Right, that's going to be a really useful equation. So let's try that. Sine to the minus 1 of glass gives us 42 degrees. That's for glass. What about water? Quickly put that into the calculator. That gives us 49 degrees. And if we look at diamond, that will give us an even smaller value, 24.6 degrees. Okay, that's quite interesting. But what happens when we go beyond the critical angle? So let's imagine now let's take our glass. Let's imagine now we're coming in at 45 degrees. That is greater than the critical angle of 42 degrees. So what happens there? Well, what takes place is you get a reflection. And no refraction. See, nothing has come through, only a reflection. And of course, according to the laws of reflection, the angle of incidence must equal the angle of reflection. So this is greater than critical angle. Okay. So if you're greater than the critical, so it could be any position here. It could be anything from 42, which is the critical angle, all the way up to 90 degrees. If you're greater than the critical angle for the material in question, this one is glass, you will get a reflection. In actual fact, we say that you get a total internal reflection, hence the title of this lesson. So if the angle is greater than the critical angle, then total internal reflection occurs. TIR. Okay, let me just do a quick little resume of that. So if the angle is less than the critical angle, you get a refraction. If you're on the critical angle, it refracts at 90 degrees. And if you go beyond the critical angle, so if theta is greater than theta critical, then total internal reflection. Okay, so I hope that makes sense there for what total internal reflection is. It's a small extension on what we've learned previously. Let me show you an example though of how this comes into practical use. Let's imagine we have a prism, a right-angled prism of glass. Light comes in and strikes that surface. What's going to happen when it strikes that surface? So here's the incoming beam. That's meant to be vertical. This is meant to be at 90 degrees. This, of course, is glass. What's going to happen? Well, we know that the critical angle for glass is going to be sine to the minus 1 of 1 over 1.5, giving us 42 degrees. We know that the normal, according to this position here, if we do the sums, is 45 degrees. So therefore it's bigger than the critical angle. We will get a total internal reflection and light passes out at 45 degrees. Now that's really interesting. Optical instruments may choose to use this rather than a mirror, because a mirror is a piece of glass with a certain thickness. So if light were to come in, it would refract into it, refract out of it, and then refract again. And that loses optical qualities. So this perfectly reflects in all instances. Okay, what about another use? Well, another use would be, and I'm going to draw this much bigger than it really ought to be, is an optical fiber. Or an optic fiber. Light that's passed in, by the very nature of the design, the small aperture of the end and the length, means that every striking of the surface will be bigger than the critical angle. And bigger than the critical angle means that light will effortlessly pass down and out the other side. I'm sure you know what optic fibers are used for. They send digital information at the speed of light from one end to the other end. And it's really, really useful for doing so. I mean, interestingly, optic fibers are often clad in a material around the outside. So you get this material around the outside, this cladding. However, it's not, intuitively you might think to yourself, oh, well that's to stop extra light coming in. It's to stop the light getting out. But it doesn't need that to stop the light getting out because the physics inside here says it's totally internally reflecting. So what the cladding does is it stops light getting in and disrupting the signal that you have inside. It's important that you keep that signal clear inside because it's sending all the interesting information down. Moving quickly on, I suppose that gives rise to talking about digital signals and why they're so important when it comes to optical fibers. Well, digital signals are a series of ons or offs. It doesn't matter how long the on or the off is, but we have at the top here on, or a 1, and at the bottom here an off, or a 0. These build up binary signals. You can encode every number from 0 right up until millions and millions with a series of zeros and ones in a binary language. So all of information that's sent through optic fibers is a series of digital signals either on or off. lit or not lit, light, not light, light, not light. And those signals come through a little bit like Morse code, but something even simpler than Morse code, a binary signal. Now, the wonderful thing about that, as opposed to, so if this is a digital, as opposed to analog, which is how most things were sent, and my voice is analog. What analog is, it's a series of waves that reflect the amplitude of the wave over a certain time period. It's continuously varying. Whereas, of course, digital is just on or off. There is a staggering amount of information held in analog. Digital, you can dictate how much information you hold, because you can say to yourself at what quality I want to hold the information for. But what's really interesting is the entire world has moved towards digital signals now. Digital signals are by no means easy to interpret or to create, so what on earth is the point in moving to a digital signal as opposed to an analog signal? I suppose one of the major advantages are, so these are the big advantages. And those being one of them, with a voice or a picture, so obviously we have sound, picture, or text. I don't just mean text message there, I mean words. Because they are series now of numbers, you can encrypt them. Security, in other words. That presents, a great advantage, and you can imagine, so you don't listen to people's phone calls, you have password protect systems, and so on and so forth. You can encrypt them. Also, because they are numbers, pictures are easily able to be adapted, so you can alter pictures easily. You can alter sounds. You can create this change of all of those bits above quite easily, because they're just a series of numbers. You're just interpreting numbers and changing necessary numbers. However, I suppose what the biggest thing is that when that analog signal, which is electrical often, and if you add that next to a noise, so just some unwanted sounds, for instance, if you were sending a electrical signal in a telephone cable next to some iron rock, which of course we know is magnetic, then the addition of those two give you this horrible signal, which then comes out the other end, and you have lots and lots of interference, which of course you don't want. However, if you sent through that digital signal and you added the noise on top, then you get through a bit of a messy signal, but one that can be easily cleared up. That still, you can remove the noise. Because you say to yourself, okay then, well, anything above that line is a 1 and anything below it is a 0. So that can be tidied up again. So you get perfect replication. That means that you'll never get a picture that deteriorates. You'll never get sound that deteriorates. So there's no deterioration at all. An amazing advantage of a digital signal. Of course, the disadvantage is that it's not easy. It's tricky. I'll say tricky, not hard. Tricky to convert into digital. And of course, you can't. If you saw ones and zeros flying past you like a falling matrix, like in the film, you wouldn't be able to interpret it. So not only is it tricky to convert into digital, but it's also tricky to convert back out into analog. So you often have an analog to digital converter, and then you go out and you have a digital to analog converter before you hear the outcome of it. But nevertheless, the world has moved towards digital signals, and that has come about from one, massive data storage abilities, because in order to interpret a text or a picture or sound, especially a picture, you need huge memory capacities. So therefore, miniaturization of hard drives and the like have enabled this, and also the quick interpretation of these signals, so fast processor speeds. Okay, I'm not completely finished with that. There's two more effects I'd like you to be aware of with waves before we finish the topic. And one of them is what happens if waves move through, so this is looking down on a wave. What happens is it moves through an aperture. Aperture. Sorry for the spelling there. A hole. Very simply, the wave starts to spread out. This is the same effect if you had an obstruction. A wave were to come past. Of course, we're looking down on the waves here. The wave will start to move around the obstruction. This effect is known as diffraction. It means waves spreading out. Of course, the larger the aperture, with regards to wavelength, so if the wavelength is very much smaller than the aperture, little diffraction takes place. So like this, for instance, then you just get a little bit, but the more she goes through, a little bit. And I suppose a consequence of this is that if you had a door of, say, a meter wide, and then light, which has 10 to the minus 7 meters width, the wavelength is incredibly small with respect to the aperture, so therefore you don't see any difference. Light keeps on going through, or, if you want, light travels in straight lines. It's a fairly easy consequence. However, if the aperture is very much less than the wavelength, then you get large effects, large spreading out. You can imagine a harbour wall. And the waves coming in, very long waves come in, sea waves, and as they go through, they start to spread out through the harbour wall. Okay, so you just need to know about the effect of it spreading out, how it happens, and therefore whether diffraction happens or not. Good, and the very last one that we talk about this very briefly is that as light refracts, different colours which mean different wavelengths they refract by slightly different amounts. So different colours, which have different wavelengths, have different refraction angles. So that means if light were to come in and start to refract in a more dense medium, it goes across. If you continue that effect, just by the nature of which it's refract again, what you get is you get light spreading out. In other words, let me draw that a bit better for you. These are the normals, of course. Light spreads out into the colours of the rainbow. This effect is known as dispersion. And it goes into red, orange, yellow, green, blue, indigo, and violet. The colours of the rainbow. Richard of York gave battle in vain. Yellow, green, blue, indigo, and violet. So different colours spread up, refract differing amounts. If you bend it once and then bend it again, you start to see a noticeable effect, and that is the dispersion. Okay, that's it. That should finish waves. Brilliant.